In this video, we're going to do a little bit of review of some Calc 1, Calc 2 type stuff, and then we're going to show how that applies to some Calc 2, or multivariable calc type stuff. So we're going to start by finding the area between y equals x squared minus 6 and y equals x. And as a spoiler, we're not actually going to find the area, we're just interested in setting up the integral that will do so. And whenever we have a problem like this, we kind of have two steps. We want to find the intersection points between the two things we're looking at, or more than two things. And then we want to do like a top minus bottom integral. So what do I mean by that? Well, let's start by setting up finding the intersections. To find these intersections, what I might just do is, I know y equals x squared minus 6. I know y equals x. So let's just set x squared minus 6 equal to x. That gives me a nice little thing that I can solve. Maybe I'll move x to the other side. And oh look, it looks like I can factor this into x minus 3 times x plus 2. And we see that my intersection points are at x equals 3 and x equals negative 2. We could even find the y-coordinates if we wanted to. Well, actually, the y-coordinates are really easy because y equals x. So this graph is going to look something like, well, I know that something interesting is going to happen at negative 2, negative 2. I know that something interesting is going to happen at 3, 3. This graph was x squared minus 6. So it's going to look something like this. And then we're going to have this crossing here. Roughly speaking, this is the area we're going to be integrating. Actually, I don't like that I wrote all those. So if we want to, so we found where it intersects and we drew our thing. You might remember sometimes we have to decide, do we want to integrate dx or dy? We're going to be integrating dx here. So we're going to have a little sliver with thickness delta x. And then this is where we get to the next part. We're going to be doing a top minus bottom integral. So I'm going to look at what's my top function, what's my bottom function, and that's going to give me the height of each little sliver I'm integrating. So in this case, the height of this little sliver is x minus x squared plus 6. So I'm going to be integrating these little slivers of height x minus, you know what, I'm going to write it as x minus x squared minus 6, just like that. And I'm integrating dx. And what's x going to? Well, if I kind of smush, well, that's going to help us later. What I'm going to think of is I'm going to kind of smush this whole region onto the x-axis. And what's left? Well, I'll be integrating from here to here. So I'm going to be integrating from negative 2 to 3. And when I do that, that's going to give me the integral that I want. Okay, so there we go. We could calculate that if we really wanted to. We're not going to. We're just talking about setting these things up. So how's that going to relate to setting up this double integral? So we want to calculate the integral of xy over the region R, where R is the region bounded between y equals x squared minus 6 and y equals x. And we're essentially going to do the same things. We're going to find, the integrand is just going to be xy. The hard part is going to be finding the bounds. So we'll write that out. The hard part is finding bounds. So let's go ahead and do that. How are we going to do that? You're going to find your intersections. And then I like to think of this as you're still going to have that do top minus bottom, but I'm going to also write from inside out. And this might not always be top to bottom. It might be side to side or right minus left. but in this case it's going to be top to bottom from inside out. And I'll show what I mean by that. So we already found our intersection points. It's going to be -2, -2, and 3, 3. This is the interval we're going to be integrating over. And what are we really looking at here? Well, what we're integrating between is we're going to have our y-coordinate is less than or equal to x, is greater than or equal to x squared minus 6. We can see that from the picture. In this region that we're looking at, y is between these two things. So this is going to give me my bounds for my dy part. And we'll kind of come back to that later. And now what I want to think is smush this onto the x-axis. If I'm looking at that region, but I'm smushing all of it onto the x-axis, fancier word might be projecting it onto the x-axis. What part of the x-axis am I looking at? Well, I'm looking at where x is less than or equal to 3. It's greater than or equal to -2. So you'll notice this formula had y's and x's, and this formula only had x's. And that's why I say from the inside out, sort of. Where, I don't know if that really feels like inside out, but it does to me. So basically you're going to keep smushing it down, getting one less variable each time, and that's going to be more relevant for when we're doing larger integrals. So what's this going to end up looking like? So I'm going to have a double integral. I'll leave myself plenty of space. So my integrand is going to be xy. I don't need to think about that part. But on the inside of my integral, I'm going to want the thing with the most variables. And that's going to be my top and bottom of my integrand. So since my inside was y is between x squared minus 6 and x, I'm going to have a dy on the inside. And then next, moving out a little bit, we're going to have -2 to 3 as my next one. Since that's what x is between, my dx is going to be on the outside. And this would give me the integral I would need to calculate in order to, or the double integral I would need to calculate to evaluate the integral over this region. So there we go. We've set up a double integral using kind of the same idea as we do to set up kind of these area problems. And if you think about it as this like top bottom and smushing idea, that might help you as it comes to slightly harder problems involving triple integrals, which is where we're going to go next.